Hi folks, we're going to take a look at page 270, number 31. So it's an optimization problem. I have the diagram here started. It wasn't given to us, but I'll read the question. It says a tool shed 250 centimeters high and 100 centimeters deep. Okay, so 250 high, 100 centimeters deep, and it tells us that it's built along a wall. Okay, so here's the wall. The shed is built along it, and it says calculate the shortest ladder that can reach from the ground over the shed to the wall behind. Okay, so it makes sense that the shortest ladder will start on the ground and will just touch the corner of the shed and eventually reach the wall. Okay, so we got to determine which one is actually going to be the shortest out of all the possibilities. Okay, so here I hope that you're seeing the two similar triangles. So that looks like a good place to start. The only problem is in each of these triangles I only know one side. And so if I want to work with side lengths, I want to work with ratios, I want to work with Pythagoras, I'm going to need more than just one side length on each triangle. Okay. However, if instead of working with side lengths, I work with an angle, okay, so here hopefully you can see why these two angles have to be the same, because the ground, and we're assuming the top of the shed is horizontal. So you've got two parallel lines being cut by a third line, so these two angles have to be the same. Okay, and the reason why this could be useful is that when we work with our primary trig ratios, you just need an angle and one side. Okay, so in order to work with the two triangles, I'm going to split up the length of the, or the height of the ladder into these two pieces. Okay, and here in this left-hand triangle, I see that I can work with sine. So I have that sine of theta is equal to opposite 250 over hypotenuse, which is x. And in this right-hand triangle, I can work with cosine. Okay, so cosine of theta is going to be equal to adjacent 100 over hypotenuse, which is y. Okay, and our equation or our function for the height of the ladder is just going to be x plus y. Okay, here height given in terms of two different variables, so I need to write these in terms of one variable, and that single variable is going to be the angle that the ladder makes with the ground. Okay, so we can rewrite height as x, do a bit of rearranging here, so x can just be written as 250 over sine theta, okay, plus, and y, again, do some rearranging, 100 over cos theta. Okay, so this is the model that I was looking for. Let's look at the restrictions on the variable. So theta, well, clearly it's got to be greater than 0. It has to come up the ground. Can't be less than 0. Can't go underground. So theta needs to be greater than 0. Okay. And here makes sense that it definitely can't go beyond 90 degrees or pi over 2, because it doesn't make sense to have the ladder going in that direction. Okay, so less than pi over 2. So notice here, because I'm going to be taking derivatives, I want to work with sine and cosine in radians, since that's where we have our nice derivatives for sine and cos. Okay, so here we go. We have everything we need. Now we just have to do the calculus. So step one is to take the derivative. So I'm just going to rewrite this. Now I notice that, 1 over sine theta is just equal to cosecant theta, but I'm going to solve this problem without trying to remember those derivatives. Okay, so I'll just rewrite that as 250 times sine theta to the negative 1 plus 100 times cos theta to the negative 1, and I'm just going to use the chain rule here. Okay, so h prime is just going to be equal to negative 1, so negative 250, okay, times sine theta to the negative 2, and then times the derivative of sine theta, which is just cos theta, plus, okay, here again we've got that negative 1 that's going to come down, so negative 100, okay, times cos theta to the negative 2, and then derivative of cos theta is negative sine theta. Okay, so as we're preparing for an exam, I'm going to try to do this question to use as little as I possibly can. Okay, so we're just using the derivatives of sine and cos and the chain rule. So h prime, let's clean this up here. Well, what do we have? We have negative 250 cos theta over sine squared theta, and then here two negatives go, so plus 100 sine theta over cos squared theta, And of course, I want to set this equal to 0 to find my critical points. Okay, so I'll do a little addition here. So we have negative 250. So here, this cos squared will multiply there to give us cos cubed theta. This sine squared will multiply there to give us plus 100 sine cubed theta. Okay, all over sine squared theta cos squared theta. Okay. So here, let's, in order for this to be equal to 0, the numerator has to be equal to 0. So I'll save myself a step by bringing the minus 250 cos cubed theta to the other side. So we need 250 cos cubed theta to be equal to 100 sine cubed theta. Now, you might wonder why would I just bring it to the other side? Well, because the cos cubed, sine cubed, there's not really too much I can do with that. But what I figure is that if I divide cos cubed, I end up with sine cubed theta over cos cubed theta. And here, let's divide 250 by 100 on the other side, so 2.5. But this is just equal to tan cubed theta. Okay, so I can start solving by first taking the cube root. So tan theta is going to be equal to, and this is where I take my calculator and do 2.5 exponent 1/3, and we have 1.36 about. Okay, and then I'm going to take tan inverse of that, so tan inverse of that previous answer, and that gives me about 0.94. Okay, I'll keep 2 decimal places, so 0.94. Okay, so it looks as though the angle that's going to give us some optimal ladder height is going to be the angle 0.94, but of course we have to check whether 0.94 actually represents a minimum. Okay, so here we know we were going from 0 to pi over 2. Okay, so 0.94 is somewhere in between. So here let's pick 0.5 to the left and let's pick 1 to the right. And here's my derivative, but I'll use this simplified form here, okay, because I realize that my denominator is always positive. So I just have to check the numerator. Okay, so let's do that. Let's do negative 250 times what comes first, cos of 0.5 all cubed, okay, and then plus 100 times sine of 0.5 all cubed, okay, and we end up with something negative, so that's a good start because I do expect or hope that this is going to give me a minimum. Okay, and now let's put 1 into that expression, so negative 250 times cos of 1 cubed plus 100 times sine of 1 all cubed. Okay, and we get something positive. So this indeed gives us a minimum. Okay, but of course what we're looking for is we're looking for the actual height of the ladder. I'll go back to my question and check, and it says, yeah, calculate the shortest ladder. So we're looking for a height. So now I can take my answer. So we had the height, remember, was given as x plus y, but that was in turn given by 250 over sine of theta, so sine of 0.94 plus 100 over cos of 0.94, and so let's calculate that here. Okay, let's go into the light. So let's get rid of that. So what do we have? We have 250 divided by sine of 0.94, okay, and then plus cos, oh sorry, I'm going to do 100 divided by cos of 0.94. Okay, and that gives us about 479 centimeters. Okay, so there we have it. So, bit of a long problem, probably a little tougher than you'd get on an exam, but it just sort of shows you the different steps that one has to follow. So step number 1 is to determine your model. Okay, get a good diagram, figure out what you're going to need. We saw that Pythagoras, similar triangles themselves weren't going to help. We needed to work with an angle. And we were able to get a fairly easy function to represent these two parts of the ladder. Okay, once you get your model, figure out what your restrictions are, and then from there it's just about doing the correct calculus. Okay, so take the derivative, set it to 0, find your critical point or critical points that are in your domain. Okay, and here check what type of optimal value you get. In this case here was a minimum, which is what we were looking for, and then from there check what they're actually asking you to do, which in this case here was to determine the minimum height. Okay, so I'll just kind of leave this here for people to take a quick look at in case they're only looking at the end. Okay, and there's a solution to that one there.